This is a short video about how summation notation works in statistics. You may remember doing summations in pre-calculus or calculus with this capital Greek S, sigma. And in pre-calc and calculus, you always had these indices. You might have something that looked like this, for example. And this meant I is going to go from 1 to 5, and then you're going to put an I here. I equals 1, I equals 2, I equals 3. So you get 2 times 1 plus 5 plus 2 times 2 plus 5, and so on until you've gone, I has gone step through all the way from 1 to 5. And so then you add all these expressions up. So this is I equals 1, I equals 2, I equals 3, I equals 4, I equals 5. You need to add all those up. In statistics, we don't use the summation notation in exactly the same way. Because in statistics, what we often want to do is we want to add up all of the data values. We just want to run through the data values and add them all up. We don't have a formula here that we want to plug numbers into. We simply want to say, if we have some data set x1, x2, x3, maybe these are some numbers, and we want to get their mean, x60 or something like that, and we want to get their mean or something like that. Well, you know how to average something to get the mean. You add them all up and you divide by the number of things here. In this case, this would be 60. So the way we use summation notation in statistics to represent this, we still use the sigma, but then we just write sum x like this. X here represents any one of these things. If we were doing like a pre-calc notation, we'd write like x sub I and then have I going 1 to 60 or something like that. But all of this is redundant in statistics because we always do our sums across the entire data set. So we don't need to say put the I here. We don't need to put the 1 to 60 here. All of this is unneeded. It's always go across the whole data set. And so we simply write the summation sign and we just put x. And this in statistics means add up all the x's. This is how the summation notation is used in statistics. If we wanted to add up all, we could do this. Then this would be add up all the. This would be add up all the x squared. So this would mean square each x, and then add them all up. So let me give you, for example, 3 examples of this. The mean, which is represented with a symbol x bar, can be defined like this. Remember, n always represents size of the data set. So this just says add up all the x's and divide by n, and that's how you get the mean. Okay. The variance, which is abbreviated VAR sometimes, what you do is you take each data point, subtract it from the mean, and then you square that, and you add all those up and average them. So this is how we do the variance. This is the summation notation for variance. So this says take each x value, subtract it from the mean, square that, and then add all those up. The correlation coefficient, which we've seen more recently, which is R. That's when you're dealing with ordered pairs, remember. So you have ordered pairs of values. So then you get the z-score for each x and the z-score for the corresponding y. When you have x and y in the same expression, it's always understood to be the corresponding ordered pairs. So we're going to do zx times zy for each ordered pair. You multiply those together, you add them all up, and then you again divide by n. This is some examples of the summation notation. There's some properties of summation notation that's going to be important in some of the proofs we're going to be doing. Let me review them briefly here. Properties of summation notation. Losing my focus. There we go. So one property of summation notation is if you have some constant. So this would mean if you have a number here, sum 8, sum 2, whatever like this, something that doesn't vary as you run across the data set. Well, of course, remember the data set has size. There's always assumed to be n elements. So this would be, let's say this constant here was some number k. So this would be k plus k plus k across the whole data set. And since we always assume the data set has size n, this just ends up being n times k. Second property is if we have a constant times something that does vary. Remember, this x, different heights of students, or the different
amounts of monies, or the different masses of things, or the different values of houses. These are x's changing as you go across the data set. But if k is some constant here, then by the distributive property, this would be like kx1 plus kx2 plus kx3. By the distributive property, you can factor out that k. So you get k sum x. So a constant multiplying something can be factored out of the summation. Finally, the third property that we're going to use in some of the proofs is if we have multiple terms. So we have like x plus y, where x and y are both varying. Then this would be like x1 plus y1 plus x2 plus y2, and so on and so forth. We can rearrange this sum because we can add things up in any order we like to do all the x's first and then do all the y's. So this is the same as sum x plus sum y. So this summation sign distributes in a sense. If you're doing two terms here, you can sum each one separately. And those are going to be three properties of the summation notation that we'll use in some proofs in this class.